Hello, everyone, and welcome to episode 3 of season 2 of the Wolfram Student Podcast. I'm Sam,
And I'm Rashan.
and we're your hosts.
This is the Wolfram Student Podcast, where every fortnight we dive into a new, innovative project done by high schoolers using the Wolfram language.
For this episode, let's welcome George, who'll be discussing his project on a morphological analysis of river tributaries and floodplains. Hi, George.
Hi, my name is George. I'm a senior at the North Carolina School of Science and Mathematics, and I attended the 2023 Wolfram Summer Research Program.
Cool.
Yeah.
Great to have you here.
And also, I guess, was this the most recent Wolfram Summer Research Program? Was that your first time experience with Wolfram, or have you done some stuff with it before?
Yeah, so before the Wolfram Summer Research Program, I haven't really explored much about the Wolfram language, although I've heard about Steve Wolfram and the many, many cool theories that he came up with, but I've never interacted with the Wolfram language.
Yeah,
Mhm.
that's cool. I guess camp's a bit of a learning curve, but at least they take time to explain everything. So camp is great.
Yeah, yeah, of course.
So just as an icebreaker question, we like to, just ask people what their favorite Wolfram function is. Do you have any favorites?
Yeah, so my favorite function is listplot3D. I actually use a lot of it in my project. So it's a function that is used to generate a three-dimensional plot from a list of data points. And this function was extremely handy for me for visualizing surfaces or terrains as I did a lot of imaging processing. And so basically how it works is that you input a XYZ coordinates and the positions of the matrix will determine the X, Y, and Z points on your morphological graph. And then after that, it will output a 3D surface plot. And then there's also a lot of options for it. For example, you can use mesh, color function, plot range, and much, much more.
Yeah,
Cool. Yeah,
that sounds
that's
really
super
cool.
good. Yeah, very
Cool. So do you want to give us first a quick summary about your project, what it's about, all stuff like that?
Yeah, sure. So it's actually really interesting because my project is split into two components. So the first component is it begins with the analysis of the structure of river tributaries in 2D using polygon clustering, satellite imaging, and a lot of cleaning protocols. And then we also developed respective tributary tree graphs, morphological graphs, and nodes to create a comprehensive tree and 3D model. So this part of the project was completed actually relatively quickly. So in our second meeting with Stephen Wolfram, I suggested a more profound approach to what I find interesting, which is floods. So afterwards, my second part of the project was examining the morphology of floodplains in 3D space and implementing the rational method, which is one of the oldest frameworks for floods, to create relief plots to predict, model, and visualize flooding elevation. And after that, I created a few more extensions for my project to be more applicable to users around the world.
Anyway, your summary sounded really cool. Do you want to just, I guess, dive straight into your project? Explain exactly what all this fancy graphic looks like.
Yeah, sure. So there's actually a few key components. So the first thing that we discovered was something called polygon clustering. So what we did is that we took a Google Maps and then we took all these blue things, which are rivers. We characterized it in a derivative and basically extracted all of these components into a single bitmap. And so using this bitmap, we selected and used sorting in order to separate more. We did a lot of cleaning with binarize, color negate, and dilate and delete small components. Afterwards, we extracted the whole thing using morphological graph. And then after using morphological graph, there's also this really cool function that you can use called translated reduction graph. So one of the problems that we had in our project was the cyclic components. And with these cyclic components present, we could not create any trees. And so we have to find a way to remove these cyclic components. And a cool function that we found was translated reduction graph, which makes all these cyclic components acyclic. And with these cyclic components gone, we're then able to create a tree graph. So
Hey,
this
George,
is the end.
is
Yeah,
it okay if I ask a question real quick?
yeah, sure.
So the cyclic components, so if you could just scroll up a bit. Yeah, I've actually used morphological components in one of my own functions, so in one of my own
Yeah.
projects. This is actually really cool. I think that this is the perfect application for that function. So if you want to
Mhm.
scroll up a bit, and I want to see sort of the original picture. So are you talking about these oxbow lakes, and is that what's causing the cyclic components?
No, so these are actually so before the transitive reduction, we actually only just binarized it and then cleaned the data. So
Yeah, yeah,
when we
right,
yeah when we
right.
when we transition the morphological graph
Mhm.
to this kind of image, that's when we apply the transitive reduction graph.
Right. No, I was just wondering, like, that circular thing we see in the morphological graph.
Hmm.
Um, like, what causes that? Like, is it the oxbolates, or sort of like, basically, what's the physical like thing in
Yeah,
the river system that's causing the cyclic component to appear? That you then obviously remove that with that
yeah.
function, that really interesting function you mentioned. But I'm
Hmm.
just curious, sort of what's causing that initially, that cyclic
I think
component.
I think what happens is that these small components that's disconnected from the river, when they get dilated, they actually get attached to the river as these
Right.
very like kind of peninsula like structures. And then
Hmm.
when we reconnect it back together, it just shows as a cyclic component. Um, because we sometimes we the fitting for the data isn't as accurate as we hoped, and so that's when we have to reapply the acyclic to get rid of that small little blotch.
Got it. Yeah, that makes sense. Cool.
And so another part of the first part of the project is mapping river branches on maps. And so while we did evaluate polygons, extracting polygons across a multitude of different maps with a lot of color schemes is not trivial. And so we use the functions nearest and color replace to make the association of the river's blue to our desired blue color. And so this takes the variability out of the colors that we have to extract and makes it a lot easier for us because we don't have to account for every single color and instead match the nearest blue to our blue for when we're extracting our morphological components. And so here is a large function that we coded to create this image, which shows the different branch splits. So I can walk you guys through the code. So first thing that we did is that we took the map of Paris, which is one of our one of our model cities. So what we first did is that we took a geographics and took everything into a vector. And so by using a vector, we're able to create everything into polygons. And after that, we separate the raw layers using Geo2 graphics layer, and then we set our watercolor function. So as I mentioned earlier, the watercolor function is to make different shades of blue the same blue. And then we applied the river branch map, which is basically to uh, resize every single map onto a 10 by 10 mile satellite image. And then we did a river branch map function, which is basically to take all of these components, extract them, overlay them on the Paris map, as well as delve more into the small components like morphological tree graphs, see the splits, plot the points on these splits, and overlay it on the entire Paris map too. So this whole code, basically the purpose of it is to identify the splits inside the streams through a function called stream splits and being able to map this back on the river and back on the map once again. So while this may seem like an intimidating code, it's a lot of repeats. And I think if we cleaned it better, we could have made it a lot less intimidating. And then using this code, we actually applied it and tested on simple river systems. So simple river systems might be very overlooked because you might think that if the river is simple, then it would be easier for us to apply these functions. However, sometimes the simple ones are the hard ones because these simple river systems have a lot of small components, minute components that are not trivial. And so if these components get jumbled together and make a incorrect river, that is a problem too. And so what we delved into was a model example from Jackson, Mississippi. And so again, we apply the polygon components function in which we use selects and cases to isolate the river apart from other small components. After doing this, we again use binarization. As I mentioned earlier, we use the functions binarize and flatten and took this whole river and made it into a binary map. And after that, we did a lot more cleaning, including delete small components to make one simple river. And then that's when I started delving into to see if there's more accurate representations of this river other than morphological graphs. So I created a morphological graph and compared it with the 3D reduction graph. I also compared it with the tree graph. And so some common flaws that we saw with this type of approach is that we saw that minute tributaries, so even those that are only visible, like let's say only 1% of the river, was shown in full in the tree graph. Because the tree graph cannot differentiate between a large tributary and a small tributary, it was extremely hard for us to scale how big the tributaries, the individual tributaries are. And so one of the solutions to that was to use something called stream order, which is something I'll dive into later on in my presentation. And so with that flaw in mind, we moved on into complex river systems. So complex river systems have the same problem as simple river systems. Complex river systems have components and tributaries that are overlooked rather than underlooked. And so we examined a model example from Alaska. So repeating the same steps, I'm just going to skip to the end. We found a morphological graph that is partially representative of the rivers that we saw in Alaska. So one of the one of the main components, one of the main flaws that we saw in this was that it did not account for large parts of the river, and it also counted large bodies of water as multiple rivers. And one way around that is to increase the dilation. However, when we increase the dilation for one type of river, it will ruin other types of rivers, like simple river systems. And so in the end, what we decided to do is that we decided to calibrate it based on how dense the water is. And so if the water is over a certain threshold, then it will refer to the complex river system code. And if it's under a certain threshold, it will refer to a simple river system code. And so with all of this, I presented it to Stephen Wolfram, and he was pretty happy that I was able to differentiate river tributaries just from a map. And so this is actually supposed to be my quote unquote project for the Wolfram Summer Research Program. But because I finished it pretty early with a lot of time in hand, I moved on to the second part of my project, which is I would say, a more interesting dive into floods. And so I guess I guess I'll start with a summary of why I did floods. So I used to live in the South. So I was born in Georgia. And every single year I remember a hurricane will come through or some natural disaster, and a lot of homes are swept off. Especially I think it was like 2013, 2014. It was a lot of natural disasters. And so I wanted to see if there was a better way to predict floods based on terrain data. So rather than using satellite data and not and ignoring the elevation planes, I actually incorporated the elevations, the permeability, as well as real-time information in order to analyze floods. So currently, there are also no built-in functions to predict floods, and so that incorporating this would, I guess, serve as a proof of concept for a future development of flood frameworks in Mathematica. So the specific framework I use is something called Q equals CIA, or the rational method. So using the rational method, we are able to account for three variables: the C, the permeability of the surface; I, the intensity of the rainfall; and A, the acres of land it was on, to create Q, which is the total stream rise elevation during the flood. So in order to do this, I first delved into imaging processing. So image processing is something that I feel like often underlooked in Mathematica. So I think a lot of projects dwell more into the numerical analytical side of Mathematica, but I feel like Mathematica also has a lot of uses, especially in image processing. So the first step of this section is to find a way to take satellite imagery of a geographic location using a function called geoimage, and then extracting the river basin using imaging processing like image compose and my favorite function, listplot3D. And so for this part of the project, I used the model city Juneau to model a lot of my satellite images, terrain data, etc. So I'll just start by introducing some of the important functions that you may or may not have recognized from my previous section. So one of the most important functions was geoimage. So geoimage, color negate, binarize, and image recolor. All four of these functions basically takes a satellite image, extracts the river from it by ignoring all the other images, recoloring the color because I thought black was a little ugly, and then putting it back onto the satellite image using the image compose function. And so how exactly I did this was pretty simple, really, by using Mathematica's options. So in Mathematica, there after like I guess the main part of the function, there are the options part, which is basically, I guess, add-ons. So if you think about it in like a more real world example, you get a sports car, but you can add a lot of attachments on it. And so what we first did was that we overlaid satellite image and river image, and then we used listplot 3D to plot it in a 3D image. And so listplot 3D took the geo-elevation data of Juneau, Alaska. Then it took the geo range, which is the 10 by 10 mile around Alaska. It used the mesh function to, I guess, make the peaks more stand out, and also to have these round surfaces. And I plotted all of the data, and through plotting all of the data, I also set the texture into the satellite image so it doesn't look black and white. Then I did filling on the bottom so it doesn't look hollow, and I put the filling style as opacity 1 so that it doesn't look clear. And the image size I set to 1000. Okay, so I'm gonna move on to relief plots. So again, if you recall from my first explanation of polygon extraction, I use it again. And so by extracting this color, which is the omnipresent color, I guess, in Google Maps, I use color replace to fill in the quote unquote flooded space, and I use a dynamic app module to synchronize the reflected changes made. And so through this animation, which I unfortunately had to take out because it was exceeding the max file limit uploaded to the Wolfram community, you can actually manipulate the rainfall data in order to get a set relief plot that you're going to use and transpose onto a 3D data. And so how I did it was that let's take Juneau again. I took the geo-elevation data of Juneau and I projected it automatically and used and specified the imperial units. And then after that, I create a side function here, which is basically to define my variables of the minimum elevation and the maximum elevation. This is so that the cities outside of Juneau can also use this data. Because if we were to hard code everything, then we're going to have to hard code Juneau data, and we're going to have to hard code the minimum elevation data of only Juneau and the maximum elevation data of only Juneau as well. And so this is basically some, I think, ease for transition if we're going to transition it to a more applicable cities. And so after that, I used again manipulate data, which is where you see this bar from, to manipulate the rainfall to serve as a proof of concept. And then I put this options as synchronized updating true. This is so that the dynamic app module can, which you see here, the Juneau relief plot can reflect this data to synchronize onto a map. And so after you see the flooded space by using this map, you can plot it on a listplot 3D. And so what's different from this listplot 3D versus, let's say, a satellite listplot 3D is that you can actually see where it's flooded. So it will automatically exclude the areas that's not flooded and only include the relief plot area where it has been flooded. And so if I zoom in a little, you can actually see there are the clear components in which the mountains are not flooded, and there are components much lower that are flooded. And so we thought that was a pretty cool application and a pretty good segue into creating our actual mathematical function, which is Q equals CIA. So I'll give you a quick introduction of what Q equals CIA is, its introduction, and its usages. And so mainly the rational method, or Q equals CIA, is used for determining peak discharge. And so this method is traditionally used to basically provide an estimate on storm sewers, channels, and other stormwater structures, especially in urban areas as well as rural and suburban areas. And so what's interesting about this is that, as I mentioned earlier, there are three components. So the first component, the C component, is basically the coefficients, the runoff coefficients for the rational formula. And so basically there was, I think, around 30, 20, 30 parameters based on the environment and how permeable the soil is. And so based on these coefficients, we were able to gauge how much water actually seeps into the ground and how much goes on inside the city or on unpermeable surfaces could lead to flash flooding. And so by using this data, we actually had to build something really interesting. So that's when we extracted other colors from Google Maps. And so instead of only extracting this blue color, we actually had to extract all of the possible colors, which is 8, from satellite, from a Google Map image, and portray and set a associate with all of these colors towards these permeable coefficients. And so when we did that, we can thread this and basically take the keys of all of this, all of the colors that we defined, and set a weight. So what we did with the weight was that it took the color density. So let's suppose it was in a very urban area, the color density of this gray color would be far more than, let's say, a color density of this green color, which represented trees. And so because the gray color had a higher coefficient runoff, we multiplied this number by the percentage of the color present in the satellite map. This will essentially give us a weighted mean. And so by using this weighted mean, we took the weighted mean and averaged it to create the city weight by color function. And so with our city weight by color function and averaging all of these weighted means, we're able to create a finite runoff coefficient for the entire city area map. So this was like an innovative way to tackle to use Google Maps in order to create a runoff coefficient for a particular city area. Of course, there are more accurate ways, but it will require much more data. It will probably require data like from the National Ocean like the NOAA, and a lot more real-time data as well. And so with our I calculation was the intensity. And so the intensity was quite easy to calibrate. So what we did was that we took the weather data over the past 20 years of a specific area through the weather data function. It was in Mathematica. And we're able to find the average annual rainfall measured in centimeters, which we converted to inches. And then we mapped the intensity of rainfall and set it proportional to how high that annual rainfall is using a which function. So this is one of the most basic functions, I think, inside the whole code, which is basically taking all of this data, setting different parameters for the which function, and calibrating the intensity. And lastly, for the irrational method, we did the A calculation, which is the acres. Very self-explanatory. 20 miles squared is equal to 256,000 acres. And so we applied this. We combined everything to get a final number for Juneau. So what does this actually mean? So this means that there's roughly 1,422 cubic feet per hour for a flash flood event in Juneau, Alaska. And so by using this data, we can again take what we know, which is a relief calculation and integration flood analysis that we did earlier, incorporate the number that we got from our Juneau total river increase, and finally plot it all into this listplot3d function. So this listplot3d, I guess, is the culmination of the second part of my project, which is basically to implement everything we know about relief plots with one additional tweak from genototal river increase here. So the plot 3D range will then show a extra layer, I guess, in a sort, ranging from the minimum increase to the minimum increase plus the total river increase that we found from our rational method. Again, we tested on simple river systems, the same one from Jackson. We saw, all of this code might seem a lot more menacing than it is, but it's just a lot of repeats. And if we cleaned it, it would probably have been around 3 lines. But in the end, we saw in the flash flood events for Jackson, Mississippi, it will rise quite far. And again, we did another complex river analysis system, this time again in Anchorage. And we saw that if the flash flood was to occur in Anchorage, it wouldn't be affecting as well. This actually made a lot of sense considering that Anchorage is very dry and does not receive a lot of precipitation, whereas Jackson, Mississippi does receive a lot of precipitation as well. And so I guess at the very end, we just try to tie everything together using what we know from our stream orders and overlaying this stream order onto our floodplain to create a cool graphic like this. And again, as I mentioned earlier, we did do a few extensions. So one of the extensions was a population density model to see which areas will be the most affected by this flood. Again, this code is a lot more menacing, but basically what we did is that we created a which function in order to calculate for the texture density, which correlates to color, and the color will be keyed in onto a combined image, which is an overlay basically. And lastly, the last interesting thing I would like to talk about is a large scale modeling. And so basically this takes the certain width of certain rivers and tributaries and determines the length of notable bridges across the river. And so this can basically, I guess, model where floods are like flood banks are most likely to get destroyed in a case of flash floods, because it shows where the river is the widest and where it's most likely to be breached are the white dots, because that's where the rivers are the most narrow. And in conclusion, so again, to reiterate, in conclusion, my project first established a framework for detecting river tributaries, which is very interesting because rivers are actually not geo-entities in Mathematica. They're only entities. And so being able to extract this geographic data from rivers is something pretty novel. And we also established nodes and river tributary branches, created trees for river tributaries, before finally combining everything together for a floodplain analysis, in which we examined geographic elevation data using a specific framework called Q=CIA, before finally analyzing population density and creating pure and honest functions to generalize all geographic locations. Lastly, we combined our two findings to create a comprehensive 3D model that models both our river tributary splits and floodplains. Yeah.
Yeah. That looks
Cool.
really cool. Thank you for
Yeah,
your
that was
project.
really, yeah, that was, I mean, your explanation was really, really helpful for, I'm sure anyone who's trying to understand this, it can be kind of tricky at first glance to understand why everything's being manipulated in the way it is, or so what the steps are, especially because, and I'm sure you know this, but like a lot of, a lot of like sort of projects done on a tight timeline like this are maybe they don't have the cleanest code because that takes like extra effort, and when you're just like watching things together and making it work, which did happen to me at camp a fair bit when I did that 2 years ago. So yeah, doing that definitely it helps to just have an explanation to code. So thanks for that.
Yeah, thank you, Rishan. Yeah.
Yeah.
Sam, yeah.
So really cool to see everything you've done with this. So I guess I'm just curious, do you have any future steps for like how you want to take this project specifically, or maybe other work with Wolfram language?
Yeah, so actually a very challenging part of this project was examining Strawler stream order. So that was what I spent 3 days on, Strawless stream order basically classifies and ranks rivers and streams based on the branching. And so it was introduced in 1950s to better characterize rivers. And so it will follow first order, second order, third order, in which smaller tributaries will join to form bigger tributaries. And so these tributaries, if you're going to do an iterative step, is actually extremely hard to identify because you're going to have to tell the program to recalculate every single time there's a new tributary. It's also very time intensive too. And so that's probably something I would like to work on more in this project. But I think outside, I'm probably thinking of working a lot with chemistry because I really like chemistry and seeing all these really cool functions with chemistry and Wolfram being its nature being allowed to pull real world data directly into our computations is really exciting, I feel like.
Yeah, that's really cool. Chemistry is definitely interesting. And it's like, I guess, a bit of a change from our current project, but yeah. Okay, thank you so much for coming on, and sharing your project with us and all your really great explanations about how all of this works. Because I've definitely learned a lot.
Yeah.
Thank you too.
Thank you. Yeah,
Thank
have
you.
a great
Have a great
day.
day. Thanks for listening to this episode of the Wolfram Student Podcast. We hope you learned something new and took away insights from today's discussion. If you want to be featured in a future episode, fill out the form at tinyurl.com/WSP-S2-interest.
And be sure to tune back in 2 weeks' time to hear our next episode. Once again, thank you for listening to this episode of the Wolfram Student Podcast.